Good. Okay. Now, can anybody think of any situations in real life that will follow this kind of curve? So continuous, but anything that will follow that kind of curve? Yeah, weights. Any others? Heights. Time. Why time?
Where time? Time is continuous.
Time is absolutely continuous. Why would it follow this shape, though? Can you refine? Because time in general won't necessarily follow that shape.
No.
But perhaps times to run a race would. Yeah, few people will be really quick. Few people will take long, but the majority of people will be somewhere in the middle. Does that make sense? Just refine the random variable slightly. Good. Any other suggestions of where of real life situations that follow this shape? Traffic, temperature, any others, boys? Income? Yeah, absolutely. Yeah, good example there. It's basically the idea, right, that you've got two tails. Okay, you've got two tails, left and right. These are kind of outliers, if you like. The majority of your data will lie somewhere close to the middle. Is that okay? So the majority of data will lie somewhere close to the middle. So this tail out here represents sort of really small values. This tail up here represents really big values, but the majority of data lands here. Okay. So if I take the example of height, okay, few people really small, few people really tall. The majority of people are kind of average height. Okay. And this here describes the spread of the distribution. If you know what your mu is, if you know what your expected value is, and if you know what your standard deviation is, then you would expect the majority of your data to lie within about 3 standard deviations of your mean. Okay? So actual fact, if I have a random variable, which I know is normally distributed, okay, the only 2 parameters which I need are the expected value, so the mean, okay, and I also need, well, I can either go standard deviation or variance, okay? Let's say in this course it's going to be variance. So the number which goes here is going to be variance, okay? It might be different depending on where you look, like the books which you look, but in this course and in the textbook for this course, it will always be variance that goes here. Is that okay? So if this is your random variable, it's going to be normally distributed. These are the 2 parameters which you need to define your normal distribution. You need the expected value and you also need the variance. Okay? And you can see that's kind of where we came from right from the very start. Now clearly, there's lots of situations in life that follow this situation. Okay? Lots of situations in life. And in fact, most situations follow this shape. So because it's most situations, we say it's normal. Right? So normal just means most situations. Yeah? So because most situations follow it, hence it becomes the normal distribution. Yeah? Okay, good. Now, like I say, this thing here, so you remember with a probability mass function or probability density function, we write lowercase f of x. Okay, that's the probability that an outcome is going to happen. Or in this case, I should write r because that's your outcome. Okay, r. Okay, so f of x, f of r, whatever you want to say. Okay, so if it's a probability density function or probability mass function, it's lowercase. Now, this wasn't too bad for a binomial or Poisson, because actually we could calculate an outcome relatively straightforward. Have a look at that though. That's a messy formula. It's a horrible formula to use, in fact. Yeah. So I would not expect you to say, what's the probability? So given a normal distribution with some mean and some variance, what's the probability of obtaining 3 as an outcome? Okay. I would not expect you to stick 3 into this formula because it's messy. Instead, what we tend to do are cumulative values instead. Okay. So cumulative values. Let me do this in blue. Okay, cumulative values, right? So instead of saying what's the probability that x is equal to some value, I'm more likely to say what's the probability that x is less than some value? Or what's the probability that x is greater than some value? Or what's the probability that x is between 2 values? Does that make sense? Yeah, so I'm more likely to look at cumulative values, so successive values one after the other, rather than just dealing with a single value. Okay? Now clearly if I'm dealing with cumulative values, I'm not going to use a probability density function or a probability mass function anymore. I'm going to use the cumulative distribution function. We've met this before. Okay, so if you remember, if lowercase f corresponds to probability mass function or probability density function, capital letter F corresponds to the cumulative distribution function, which is simply the probability that x is less than or equal to that value. Is that okay? So you remember those relationships? Yeah. Now I've got a question for you. I've got a question. It's quite an important question. With discrete distributions, okay, if I was talking about the probability that x is less than some value. So for example, if I said for a binomial distribution, what's the probability that x is less than 3? How would I calculate that? Yeah, so the probability that x equals 0, plus the probability that x equals 1, plus the probability that x equals 2. Fantastic. If I change that to less than or equal to 3, what do I need to add on? Absolutely, x equals 3. Okay? Now here's my question. If I do the same thing with cumulative values, can I do this anymore? So if I do, sorry, not cumulative values, continuous values, can I do this anymore? Why not?
Because how about 1.1, 1.2?
Absolutely, and 1.01 and 1.001. So because there's an infinite number of values between these two things, I can no longer add on the probability that x equals some value. Okay? Now, fortunately, with the normal distribution, there are these things called tables, okay, which basically corresponds to the percentage of values that you've had up until that point. I'll show you how to use those in due time. So effectively, this thing, you no longer add on x equals 1, or x equals 2, or x equals 3. You have to use tables instead, which corresponds to the percentage of values that you've had up until that point. But I'll talk about that in due course. The thing which I really wanted to talk about was, in general, with a discrete random variable, okay, the probability that x is less than 3 is not equal to the probability that x is less than or equal to 3. We've just seen that, okay? However, if I'm dealing with continuous, if I'm dealing with continuous random variables, does it make a difference anymore? Is this still true? What do we reckon? Is it equal to, or is it not equal to? Hands up for equal. 2. Everybody else not equal? Who's not sure? Okay, so some people are not sure. Okay, it is equal to, because it's continuous. Okay. Now the reason being is because technically, this should be everything up to. So this thing here should be everything up to 2.9 recurring. You happy with that? Yeah, everything up to 0.9 recurring, 2.9 recurring. But I can show you that 2.9 recurring is exactly the same as 3. Okay, let me show you. So 0.9, I'll just do it 0.9 rather than 2.9, make the maths easier. Okay, so I'm proposing that that thing should be the same as 1. Let me show you why. If I let x equal 0.9 recurring, would you be happy that 0.9 recurring is just 0.99999, etc., etc., etc.? You all familiar with recurring? So it basically carries on forever and ever and ever. So 9 carries on forever and ever and ever. So it never quite reaches 1, supposedly, but it carries on forever and ever and ever. Now watch what happens if I times both sides by x. Would you be happy I get this? If I times both sides by x. Now if I subtract these two things away from each other, so if I take 10x and I take away x, on the left-hand side I'm just going to be left with 9x. Happy with that? Yeah, 10x, take away x, it's just 9x. If I take 9.9 recurring, and I take away 0.9 recurring, what am I going to be left with? 9. Just 9, right? The recurring bits all cancel each other out, okay? 9x equals 1, so x must be equal to 1. So if x equals 1, then 0.9 recurring must be equal to 1. Okay? So in other words, these two things have to be equal to each other. Have to be equal to each other. So with a continuous distribution, we no longer care about whether it's less than or less than or equal to. They mean the same thing. Does that make sense? But with a discrete distribution, they don't mean the same thing. That's a really important point. Is everyone happy with that? Okay? So with discrete distribution, binomial, Poisson, uniform, you have to be careful whether you're talking about less than situations or less than or equal to situations. Similarly, greater than or greater than or equal to situations. Okay? But with a continuous distribution, no longer care. Okay, so in actual fact over here, I can adapt this. This is the probability that x is less than or equal to r, and this is the probability that x is greater than or equal to r. Okay, and same thing here. Okay, so it doesn't matter whether you include it anymore for continuous. Is that okay with everyone?